Welcome to the next lesson of Module 2. This lesson is about systems dynamics. We can think of Earth's climate as an interconnected system in which the parts exchange matter and energy with one another. And something that happens in one part of the system can influence another part, which in turn might influence the first part again. By the end of the lesson, you should aim to be able to describe what's meant by the words stock, flow, and feedback. You should be able to make predictions about what might happen when a stock or flow is perturbed in some way, and you should be able to construct examples of feedback loops. We're going to start with a few warm-up questions about a party. There's some graph reading involved and some thinking about stock and flow. In this case, the stock is the number of people at the party, and the flow is the numbers of people coming and going from the party in some time period. It's a big party, and there are people arriving all the time, and there are also people leaving all the time. We're going to take a look at what happens at the party over time to get some practice with stock and flow. So here's a graph. This graph represents people coming to and leaving the party over the course of half an hour. You can see on the horizontal axis that the time period we're looking at is 30 minutes long. It's some half hour, some time in the middle of the party. The vertical axis is the flow of people. It's in units of people per minute. You'll notice that there are two sets of data plotted here. The blue line with the diamond symbols represents the number of people arriving at the party each minute, and the red line with the circles represents the number of people leaving the party each minute. Both the blue line and red line have values that vary over our half hour of time. Take a look at this graph for a bit. Okay, there are 4 questions to answer about this party. First, during which minute did the most people arrive at the party? Second, during which minute did the most people leave the party? Make sure you're looking at the right line. Okay, now the third question in this half hour. During which minute were the most people actually at the party? When was the population at the party, which is the stock of people at the party, the largest? Fourth and last question. During which minute were the fewest people actually at the party? When was the stock of people at the party the smallest? Okay, let's have a look at this graph and these data. The first 2 questions were likely the easiest, particularly if you already have practice reading graphs. You needed to find the highest value of the people arriving curve, and then the highest value of the people leaving curve. 20 people arrived in minute 5. That's the peak value of the blue curve that shows people arriving. And 21 people left during minute 25. That's the peak of the red curve that shows people leaving. So for those questions, you needed to identify the highest values on each of those curves. You could also find the minutes at which the fewest people arrived, which is minute 21, and at which the fewest people left. That's minute 8. The third and fourth questions are harder. To answer them, we have to imagine how the party changes over time, given fluctuations in numbers of people leaving and arriving every minute. Notice that for the first 13 minutes, the numbers of people arriving are always higher than the numbers of people leaving. So we're getting more and more crowded at the party for each of those 13 minutes. The area between those 2 curves represents the addition of people over that time period. And then in minute 14, more people leave than arrive. And for the rest of the 30 minutes, the party thins out with the fewest partiers left at minute 30. During each minute, between minute 14 and 30, the numbers of people leaving exceeds the number of people arriving. Again, the area between the 2 curves is helpful. It represents the net loss of people from minute 14 to minute 30. We don't actually know anything about what happened at the party before our particular half hour, nor after. But notice that the orange shaded region on the right is larger than the blue shaded region on the left. Comparing these, you can tell that there are fewer people at the party at the end of the 30 minutes than there were at the beginning. We've had a net loss of people during this half hour. The purpose of this party exercise is to practice thinking about how the balance or imbalance of flows over time, in this case, people coming and leaving, changes the stock. It's the historical combination of stock and flow that determines the state of the system at any particular time. Let's talk more about stock. A stock is the amount of something, somewhere, at some time. The amount of food in your kitchen is a stock. The number of bicyclists in a city, that's a stock. Prisoners in prison, that's a stock too. A stock can also be something that's harder to count, like water in a bucket, or water in a cloud, or helium in a balloon. Or it could be something completely intangible, like goodwill, or memories, or influence within an organization, all of which can be gained and lost. As we saw with the party, stuff flows in and out of stocks. We define a flow as a rate at which stuff adds or subtracts from a stock. Since flow is a rate, there's always an element of time included. For example, we might have apples picked per hour. That's the rate at which apples flow out of the stock of apples on the tree and into the stock of apples in the basket. During the melting season in the Arctic, we could measure sea ice melted per month. Other examples are, say, fish born per year, or knowledge in your brain gained or lost per decade. There are two types of flows. There's inflow and outflow. Inflow, as the name implies, is the rate at which stuff flows in, and outflow is the rate at which stuff flows out. The amount of stuff in any particular stock can change over time if the inflows don't match the outflows. Let's take a look at a classic analogy for systems dynamics, which is a bathtub. We'll start with no water in the tub, so the stock is 0. There's a plug in the drain, so outflow is also 0. Now let's turn on the faucet. As you'd expect, if you've ever prepared a bath, the water level rises over time, and it rises at a rate that's determined by the rate of inflow from the faucet. Okay, let's turn the water off. The drain is still plugged, so the outflow is still 0, and now the inflow is also 0. Since the flows are now equal, the water level, representing the stock, stays constant. Now let's open the drain and see what happens. Inflow is still 0 because the faucet's off, but now outflow is greater than 0, so the water level falls over time. But let's turn the faucet back on again before the tub completely drains. If we turn the faucet on so that the rate of water flowing in equals the rate of water flowing down the drain, then the water level stops dropping and it stabilizes. Inflow equals outflow again. Only this time, the flows are non-zero. Let's block the drain a little bit so that inflow exceeds outflow. Watch the water level rise. Now let's open the drain further so that the tub is draining faster than the faucet is adding water. Watch the water level fall. If you've ever been in a position where you had to bail out a leaking boat, you have some experience with the balance of inflow and outflow. To summarize stock and flow with the bathtub, the stock, that's the water level in this case, at any moment is the result of the combined history of inflow and outflow. At equilibrium, or steady state, inflow equals outflow. We can have equilibrium at a wide range of different water levels. But if inflow is not equal to outflow, the stock will change. Now we'll take the bathtub analogy one step further to get us into the world of feedbacks. In a bathtub, the rate of water leaving through the drain depends partly on the water level itself. When the water level is lower, the tub drains more slowly. Let's start with the tub about half full, at equilibrium, so that inflow equals outflow. Now let's crank up the faucet to double the inflow, which will create an imbalance and cause the water level to rise. But as the water level rises, the pressure on the drain increases, so the outflow also increases, slowing the water level's rate of rise. What ends up happening is that the water level rises to a point where the pressure on the drain causes a rate of outflow that exactly matches the inflow. It's a new, higher water level, but we're back at equilibrium. This is an example of a feedback in which the amount of a stock influences a flow in or out of that stock. And the flow, in turn, feeds back to influence the stock. In this particular case, we're looking at what's called a stabilizing or balancing feedback, a feedback that brings the system back toward equilibrium. So, flow depends on stock, depends on flow. Feedbacks happen when some perturbation occurs and the system responds. It responds either by amplifying the perturbation, pushing the system even farther in the direction of the perturbation, or the system responds to counteract the perturbation, stabilizing the system, like the response of the drain coupled with the stock of water brought the tub to steady state. A perturbation could happen to either the stock or the flow. The ramifications then feed back between the two. In the climate system, you can think of feedbacks as processes or a sequence of processes that both respond to temperature changes and, in turn, influence temperature. So they have to both respond and influence. For example, imagine a glacier. It's a bunch of white ice. At equilibrium, the stock of ice in the glacier stays constant. Some is added every year through snowfall, and some leaves each year through melting or calving of icebergs. Imagine a perturbation in temperature that makes Earth a little bit cooler. With cooler temperatures, the glacier might grow a little. We know that clean white ice reflects solar radiation back to space pretty well. It doesn't absorb a lot of incoming energy. So a larger glacier would mean a larger area covered with ice, which means more solar radiation reflects directly back to space without being absorbed. So that will cool Earth's temperature a little bit more, which helps the ice sheet grow bigger, which helps cool the temperature more. This is an example of an amplifying feedback. It's a response to a perturbation that pushes the system in the same direction as the initial perturbation pushed it. To generalize, if something caused global temperature to increase, an amplifying feedback would increase global temperature further, which would keep the feedback process going. You can imagine the ice sheet in reverse as well. If temperature goes up, the ice sheet will melt a little more, decreasing the area covered by reflective ice, which in turn helps Earth warm a little bit more. This is also an amplifying feedback. A party can grow with feedback. Maybe a small party attracts attention. More people come. The party attracts more attention and more people come, etc. Let's take a look at a stabilizing feedback in the climate system. The Earth itself is at some temperature and it emits energy. The amount of energy objects emit depends on their temperature. Warmer objects emit more energy than cooler objects. So if, for some reason, the inflow of energy to Earth's surface increases, warming Earth a little, as a now warmer object, Earth would respond by emitting more energy than before, increasing the energy outflow to match the new level of inflow. By emitting more energy, it helps stabilize its temperature and brings the system back toward equilibrium. That equilibrium might be at a different temperature than it started with, but it would be a stable new temperature until, of course, the next perturbation. This is similar to the bathtub, which could have many different stable water levels. This feedback involving radiation is actually the most important stabilizing feedback in Earth's climate system. To summarize stabilizing feedbacks, they're a response to a perturbation that pushes the system in the opposite direction as the initial perturbation pushed it. To generalize, if something caused global temperature to increase, a stabilizing feedback would respond to counteract the temperature rise, which would stabilize the system, though not necessarily at the original temperature. Imagine that the party gets too crowded, so people don't like it and they leave, until the party reaches a comfortable size again and people stop leaving. That would also be a stabilizing feedback. Just as a side note, some of you know amplifying feedbacks as positive feedbacks and stabilizing feedbacks as negative feedbacks. That's fine if you know that terminology. In this course, we'll use amplifying and stabilizing because the words positive and negative feedback have everyday meanings that are different from their scientific meanings, and there tends to be confusion around those terms. In summary, Earth's climate system has lots of different stocks, lots of different flows among those stocks, and many feedback processes. Some feedbacks in the climate system amplify perturbations, and some feedbacks stabilize the system after a perturbation. We've described two important climate feedbacks, an amplifying one involving ice and reflectivity, and a stabilizing one involving Earth's temperature and the amount of energy it radiates. Keep your eye out for feedbacks in the world around you. You'll encounter them everywhere if you look. We'll examine more climate-related ones later.